Okay, today 11.1 Intro to Limits, finding limits using tables and graphing calculators and graphs. So you can see I have my graphing calculator here. You might want to get yours out as well. I'll give you a little second to do that. You might have to hit pause because I am moving on. Okay, 11.1. Hopefully you had time to watch that calculus phobe. I wanted to watch it in class, so I'm hoping that we did. If not, hopefully I'll get a link up to this playlist in our YouTube channel, The Wilkin Way. So, consider the function f of x equals negative x squared plus 4 as the values of x get close to 1. So we've already kind of seen this idea of get close to 1 when we did that continuity test. So first we're going to graph negative x squared plus 4. So this is a parabola. That's the parent function. There's a negative out in front, so it reflects over the x-axis. And then everything gets shifted up 4. So what it ends up looking like is this right here. So there's our upside down parabola. What we're going to do is consider it as we get close to 1. So on our graph is right here. But here's x equals 1. The values of x get close to 1. So I'm going to underline that because sometimes students are like, why are you just doing 1? This was arbitrarily chosen, right? I could do it to 2 or negative 1 or 17 or whatever, but for our purposes, we're going to do 1. And then in your graphing calculator, you're going to hit y equals, and then don't forget the negative, not the minus, negative x squared plus 4, graph. There we go. There's our parabola. Okay? Obviously, we have a different scale, but we're aware of that, so we're good. Okay, so then we're going to be moving on to from the left and from the right, and I'll show you what to do in just a second, but before I do that, I need to give you the values that they use in calculus. So when you go from the left, you start with 1 unit away. So if you're going to 1, so I'm going to draw just a quick number line up here. Here is the number 1. What is 1 unit to the left away? That would be 0. And 1 unit to the right is 2. So you're going to start with 1 unit away in each direction. So it's plus or minus 1. Okay? So plus or minus 1 unit. And then you're going to only go, we're trying to get closer to 1, so these values from the left have to come in this way, and these units from the right have to come in from there. So they're coming from the right towards 1, these are coming from the left towards 1. Another way to say that is the values on the left versus the values on the right. So the next unit they use is half a unit. So what is that labeled? You can see it graphically, but that's 0.5, and then over here, it would be 1.5. So to calculate that, you just do plus or minus 0.5. So 1 plus 0.5 and 1 minus 0.5 from whatever x value you're approaching. Then in calculus, we're trying to get even closer, so we do 0.9, which is like right here. And then we do 1.1, which is on the other side coming in from the right. So that would be plus or minus 0.1. Okay, I said 1 and I wrote 0.9. That's so weird. How our brain works. I must have just been thinking something different. Hey, okay, no big deal. 0.1. And then we're going to get even closer. We're going to go, so this is 1/10 away. We're going to go 1/100th away, which is plus or minus 0.01. So that would be 0.99 from the left and 1.01 from the right. Getting ahead of myself here. And then we even have to do a 5th one, which is 1,000th. So again, why are we getting so close? It's part of proving that as you get closer and closer to x without actually equaling the x, that you approach a value. And you'll see more of why we need to do this in a second. So how do we figure out what these y values are? We have 10 of them. We have 5 from the left and 5 from the right. So we can plug in 0 into x squared. That's 0. Times it by a negative, still 0. Add 4. This is 4. Now let's do 0.5. 0.5 squared, okay, 0.2. What? We could do that. We could even use our calculator to do it, but let's use something even cooler. So graph the function on your graphing calculator, then we hit graph and then hit trace. So hit this trace button right here, trace. And it pulls up some numbers and you can just start typing in x values. I am literally not doing anything other than typing 0. And it pops up x equals 0, and then I hit enter, and it tells me what y is. And now I'm going to do my next one, which is 0.5, and I'm just literally going to type in 0.5, enter, and look what it is. It's 3.75. So I don't want you to round on any of these for what we're doing, so just keep going, write the whole entire number, even in your homework, and then let's do 0.9, 0.9, enter, and you can even see on the graph it goes to where it's at. This is 3.19. And then when we hit 0.99, we get that. Whoop, only 2 nines. And then when we hit the last one, 3.001999. You do have a problem on your test that says use the table to find the limit, so you want to make sure. So look at this. As the x's are getting closer to 1, what would you say the y's are getting closer to? This looks like it's approximately 3. So let's see if it's approaching that same value from the right. So again, type in 2, get your value, it's 0. Type in 1.5, get your value, 1.75. Okay, you guys get the picture. I can't keep typing those in. Yeah? Oh my goodness. As x is coming in from the right and getting closer to 1, what are the y values getting closer to? Approximately 3. So how we can represent that using a math notation is using limits. So we say the limit, LIM, so you don't have to write the whole word, and limits are a mathematical operation. It's not the same as taking square root or adding, but it's one of those kinds of operations. So again, we don't like it because we're using a word instead of a symbol, but it's a mathematical operation. So the limit as x goes to 1 of negative x squared plus 4, and you do need the parentheses on that, equals 3. Because when we come in from the left and the right, we approach the same value. Isn't that nifty? So the definition of a limit, you're like, we watched that. This is key. It's the intended height of the function, not necessarily the actual height. So this is where we differ when there's a hole in the graph between undefined and a value. Whoa, I wrote undefined. Good thing I have my handy dandy whiteout. What? It's okay to make mistakes. Mistakes are how you learn. Keep that in mind. All this practice. Your brain grows more when you make a mistake than when you get the answer correct. Isn't that crazy? So if you make a mistake, just be like, oh, my brain's growing. And then hopefully you'll learn from it. And then the next time you don't make the mistake, and then you make a new mistake. So it's okay. So the notation, this is read as the limit as x approaches a of f of x equals L. Another way to think of it, as x gets closer to a, but not equal to a, remember, not equal to, we didn't ever type in 1 up here. We got really close to 1, but we didn't type it in 1. The values of x get closer to the f of x value, which was 3 in our case. And the function may or may not be defined at a. So let's take a look at these. These are kind of like weird examples, but I'm going to show you guys. Here's an x value. We know it's the x value because it's the x-axis. And then here's the limit L. So basically this is saying this. So what this is saying, I want you guys to write this because I want you to know the difference between the limit and the function value. Sometimes they're the same and sometimes they're not. So the limit here, I would say the limit as x approaches a, and since I don't have an equation, but I know that it's f of x, what's the intended height? As x gets closer and closer to a, look I can do left and right from the graph. Left, getting closer, closer, right, getting closer and closer. That height is not a number, it's a letter, it's L. Great. It's actually what it says right there, so we're on the right track. What is f of a? So this is something we've already done. When x equals a, what does y equal? L. So those happen to be the same thing. The limit and the function value in this situation are the same thing. What about this one? What's the limit? The limit as x approaches a of f of x equals, okay, so now remember, limit is the intended height, not necessarily the actual height or the function value at that point. So when I go back to look at this graph, you need to think of that table that we just did. As I come in from the left and come in from the right, what is the intended height? Like, what is it approaching? What does it intend to do? It intends to get to a height of L. Now, when I do f of a is all about what does it actually equal? What is the actual height? And f of a is 5 because when you graph it, when x is a, y is 5. Okay. Oh no, this one has a whole 2. Okay, the limit as x approaches a of f of x equals, so as I get closer and closer to that x value, my function intends to go through L. What is f of a? Well, there's no part of the graph that actually touches it, so this is undefined. So notice, this is one graph right here where the limit equals the function value. This one is where it doesn't, the limit doesn't equal the function value, but there does exist a function value. And then this one is where the limit is L and no function value is defined. Okay? Cool. So tables, now let's go on to the graph part. We're giving this nice graph. Right here, use the graph of f to state the value of each quantity. The limit as x approaches 0. So think of that getting closer and closer to 0. So as I come in from the left, so here is x equals 0, it's the y-axis. As I come in from the left, it looks like it's going to a y value of 1. As I come in from the right, same thing. So this is 1. Okay. Let's do B, -3. Okay, here's -3. If you want to give yourself a little mark at -3 just to make your life easier, you come in from the left. So I'm getting closer and closer, coming from the right, and it looks like it has a y value or intended height or a limit of 0. What about the limit as x equals 1? So here's x equals 1. If I make the same height of line, I don't really get to my graph. And you don't have to do these lines. These are just visuals to help my visual learners. But you come in, what's that intended height? That is 2. What about at -2? Here's -2. As I come in from the left, it approaches a height of 1. As I come in from the right, it approaches a height of 2. That means that the limit does not exist. That's where you get to pull out your inner mean girl. The limit does not exist. The reason why the limit doesn't exist is because we will get to this in just a second, but the definition states that when you come in from the left and when you come in from the right, they have to be the same value. So keep that in mind. Okay, next one. Use a table of values to estimate the limit. So this one I'm going to put tricky, just because there's a little bit of funness, is that a word? Funness to this. Okay, the limit as x approaches -2 of this rational function. So first thing I want you to realize is that this can be factored to x plus 2 times x minus 2 all over x plus 2. And you might think, why do we need that? You might not just yet, but what I do want you to know is that we want to be able to write things. We want to look at something and go, if I need to, I have this factoring tool in my back pocket. So what are we going to do? Well, these would cancel. And another way to write this is just x minus 2. It's just a line. But if at any point along the way it makes the denominator 0, it must be excluded from the domain. So x cannot equal negative 2. So what the heck kind of graph does this look like? It looks like this. Your y-intercept is negative 2. So the y is negative 2. And then your slope is up 1 over 1, up 1 over 1. However, I can go down 1, back 1, down 1, back 1, but I would actually have a hole right there because that's when x equals negative 2. And if you actually type this function into your calculator, which we are going to do just because we want to make sure we have to do the table, and who wants to plug this all in by hand, you're going to hit y equals, and when you plug this into your table, plug in this. So we have x squared minus 4, and I put that in parentheses because if I didn't, then it would do x squared minus, and it would only do 4 divided by x because of the grouping symbols and the way order of operations works. So group your factors and group your numerator and denominator. So hit graph. Hey, look at, there's the line I just graphed. Hit trace, and I want you to hit negative 2. X equals negative 2. What does it tell you y equals? Bam, nothing. Why? Because it can't equal negative 2, because you can't divide by 0 in math, and if I plugged in negative 2 there, that's what I would be doing. So let's pick our values from the left and the right. So the limit is telling us we got to go from negative 2. So we do plus or minus 1. So minus 1 would be negative 3, and this would be negative 1. Then we go halfway, so this is negative 2.5. Now remember, we're in negatives. Sometimes we have a hard time with that, so I'm just going to draw this up here. Here is negative 2. I need this number and this number to be 1 unit away, so that would be negative 3 and negative 1. Then negative 2.5 and negative 1.5. And then plus or minus 0.1, we have that written over there if you need it. So negative 2.1, negative 2.01, and negative 2.001. And then over here, negative 1.9, negative 1.99, and negative 1.999. How do I find the y values? Aside from plugging them in, which would be really tedious, I'm just going to hit trace and type in the numbers here. And I get negative 5. And I could sit here and type these in all day, but instead I'm just going to write them because I've already typed them in, so I know they're correct. And you can feel free to copy them because as much as I love math, I don't particularly like to waste your time. So you know what you need to do, then you can just copy this down. If you don't know how to use that calculator or you're not confident yet, then you should use the calculator to make sure you're getting these values. It's not going to hurt you to do it that way. Okay, as x is getting closer to negative 2 from the left, what are the y values approaching? Negative 4. And as x is coming in and getting closer to negative 2 from the right, what are those y values approaching? Negative 4. So we now know that, we're going to scrunch it over here, the limit as x approaches negative 2. Now, by the way, you need to follow notation here. To leave a limit, and if you just went like this, equals negative 4, that absolutely makes no sense to anybody who knows anything about math. So I don't want you to be the laughing stock of the math world. It would be like me saying the square root of nothing equals negative 4. Like you're leaving that number out. It just doesn't make sense. So don't do that. You can have proper math form. It'll be great because you understand what you're actually doing. It's an operation. So if I had named this f of x, then I could just write f of x if I wanted to kind of be lazy. But since it's not named f of x, you could name it f of x. You can just go like this and go equals f of x. and then just use f of x here. But since it's not, I'm just going to write it out and then write -4. So here's the answer right here. Okie dokie. All right, let's move on. Another tricky. Okay, this says, given this function, ooh, it's a piecewise function. Graph it. Okay, cool. 2x minus 3 if x does not equal 2. Remember when we did our boundary points, x cannot equal 2. It means it can equal anything else. So when I do, I'm going to have an open circle at, and I'm going to plug 2 in there. So that's 2 times 2 minus 3, which is 4 minus 3, which is 1. So at 2, 1, I'm going to have an open circle. So 2, 1, I got my open circle. Now I can graph the rest of my line. I go down to -3, that's my y-intercept. Go up 2 over 1, up 2 over 1, but it's an open circle. And there's my graph. Sweet. Now, if x is equal to 2, then y equals -1, which means it's just a point, so it would look like that. So now that we have the graph, we get to use the graph to find the following. The limit as x approaches 2 of f of x. So remember, limits are intended heights. So it says, as I come in from the left and as I come in from the right, my intended height is +1. Again, let me say that. Here is where x equals 2. At this point right here, I can't come in from the left and from the right. Like if I was picking table values and I said 1.9, I would be on this part of my piecewise function, right? And if I said something like 2.1, I would be on this part of my piecewise function because it meets this condition. So as I'm getting closer and closer, those values, just like up here, I didn't quite equal it, those values are going to get closer and closer to a height of 1. But at 2, specifically, what is f of 2? It's not asking about the limit. It's saying what is, when x is 2, what is y? And so when x is 2, y is -1. Okay, dokie, flip it over. So here's what I was talking about before, left-handed and right-handed limits. They're called one-sided limits. So the left-hand limit, go figure, is notated with a negative exponent, kind of. It's as x approaches a from the left is equal to L. So that's the negative. Why would they use the negative from the left? Because, you know, the negative numbers are to the left. And then a right-handed limit is to the right. So it has that plus sign. Then we go into this. This is what I said before. The limit at a certain value equals L. This is if and only if. And we're still kind of new at interpreting definitions, but we can work through it. So that's not a typo. It's if and only if in math. But the only way that this can be equal to L, the limit of this function as x approaches a, be equal to L, if your left-hand limit, you can see it's left-hand because it's negative, and your right-hand limit equal the same value. If they don't, then it does not exist. Okay? So let's take a look at some problems practicing left and right-hand limits. So here's our graph, and it says the limit as x approaches 2 from the left. So that's not -2, that's 2 from the left. So here's 2. Whoa, this is cool. So as x approaches 2 from the left, it's coming in and getting close, close, close. Its intended height is 3. And then we're going down to b. And as it comes in from the right, which is over here, it's 1. So at 2, because there's a break in the graph, and because my left and my right hand limits do not match, it does not exist. Now, if we applied this to continuity, can you see why this function would be considered discontinuous? It's kind of saying the same thing, but with a different notation. Let's go to D. Let's go to 4, which is right here. 4 from the left, okay, one number before 4 is here, so I'm going to start getting closer, and so that would be a height of 2. And then what about from the right? Oh, that's also a height of 2. So even though my graph doesn't go through a height of 2 when x is -4, it intended to. So the limit at 4, and only 4, not left or right, is 2. But h of 4, because this is the h function, h of 4 is actually 1, because that's the function value. That's the actual height, not the intended height. Okay, moving on. We're moving on to this function right here. You could graph it in your graphing calculator if you want. We'll be graphing these a little bit later in the chapter by hand. So it'll all tie together, but f of x equals 1 over x minus 4. First of all, if I asked you to graph this and you didn't have a graphing calculator, make a table. It's awesome. You can always get at least a part of your graph. So x cannot equal 0, so what's going to happen is I'm going to get an asymptote at 4. And then, again, don't stress about this right now, just copy it. Has another asymptote right here. And then these graphs like to coast along their asymptotes. So this one kind of looks like that. I'm sure you guys remember these from Algebra 2 or Math 3 if you took the honors route. So use the graph of f of x to find the following. The limit as x approaches 4 from the left. So here's 4. It's this line right here. Here's 4. This is the left. This is the right. So cool. So when I approach from the left, I'm looking at this piece of the graph. It's almost like a piecewise function, but not. So this is approaching. What's it doing? It's going to get infinitesimally closer to -infinity. Okay? And what about from the right? Infinitesimally closer to positive infinity. What about at 4? Guess what? Because the left and the right do not match. One's negative, one's positive. The limit does not exist. It's like you're forever going away from each other. So right here, we have the limits out of infinity. That's kind of what we were just showing you. The limit as x approaches a of f of x equals infinity. So what would that look like? Because this one, it was a left-hand limit to -infinity, and this one was a right-hand limit to positive infinity. So how would you actually get a limit that equals infinity? Well, look at this graph right here. What you can see is that there is an asymptote here, but the left is going to infinity and the right is going to infinity. So because the left and the right match, then the limit is infinity. And here's a picture of one where the limit would be -infinity. Again, because the left and the right match, that's what it would look like. Now this one right here says find the limit. And tomorrow we'll be learning how to find limits from equations, but right now use any tools you have available. So you can either make a table or you can just plug it into your graphing calculator and you will see I would make a table, but whatever. So what you'll see is that there is going to be an asymptote here at 0 because your denominator cannot equal 0, and there's going to be one here as well, and this graph is going to go like this and it's going to go like this. And this one says the limit as x approaches 0. So here's 0 right here. The limit from the left is infinity. The limit from the right is infinity. So this is infinity. However, what if I asked you something like this? Ooh, I'm not asking you about the limit at the asymptote. I'm asking you like right here. So as I get closer from the left and right, that one's just 1. So it doesn't mean that this graph, all of its limits go to infinity. It just means that when x is getting closer to 0, the y values are getting closer and closer to infinity. And that's all that we have for you today. So until next time, adios.